In this video we're going to take a look at some of the Pwn challenges in the picoMini CTF, which is run by redpwn this weekend. The first challenge is called clutter-overflow, and the description says clutter everywhere, not a byte to use. So we have our netcat server here to connect to once we get things working locally, and in this instance we actually have the C source code to download as well, so we don't need to open this up in Ghidra as we would normally because we'll have access to the original source. And then we also have the binary to download as well. So we download a copy of both these. I've already got a copy of them locally, so let's go and take a look. So we begin by checking the file type. We'll see it's a 64-bit executable. It's not stripped, so we will be able to see function names and things like that. We can also run checksec on it and find out what kind of binary protections are enabled. In this case, NX is enabled, so if we're able to exploit a buffer overflow and inject code onto the stack, we won't be able to execute it. But there aren't any canaries, so there's a good chance there will be a buffer overflow, which would make sense because the challenge is called clutter overflow. And pi is disabled, so each time the binary loads, it'll load at the same location in memory. If we're able to find any useful addresses or gadgets, we'll be able to use the hard-coded address, which is good to know as well. So let's go and take a look at the source code, because in this case we've been given access to that. So if we take a look at the code, we have some variables declared here at the beginning defined. We have our size set to 100, which will be 256 bytes, so that's in hex. And then we have also a goal as well, which is set to dead beef in hex. And we have this header, which looks like some ASCII art, which is going to be printed out. And then our main function here. So we have code is set to 0, we have our char clutter, so this is our buffer which is defined, and the size is going to be 256 bytes. And then it's going to print out the header, so it's going to print out this ASCII art, it's going to print out some text, and then it's going to use the dangerous gets function, so it's calling gets on clutter, which is 256 bytes, but it's not specifying how many bytes to read in, so it's allowing the attacker to enter in as many bytes as they want here to overflow this buffer. So they should have used fgets and set the size that they're reading in to be the same size as the clutter buffer. So there's we've got a buffer overflow spotted straight away, so let's have a look and see what we have down here as well. So we have a condition at the bottom which says if code, which is initially set to 0, if that equals goal, which was the dead beef, then it's going to print our flag, system cat flag.txt. And then if we don't meet this condition, so if we weren't able to get this long code to equal dead beef, then it's just going to print out and say what our code was and what our goal was, so then we can try and work out what's gone wrong and try again. So let's go and open up GDB. I'm going to open up PwnDbg, and we can go and check out that buffer overflow and see where the offset is at. So we'll open it up. We can have a look in here at the functions as well. If there were any of interest, we could quickly disassemble them. For example, a main function. We know that in the main function we want it to call this system, where it's going to call system cat flag.txt, so might be worth knowing where that is. And if we want to test out finding out where the pattern is, finding out where the offset is here of the buffer overflow, we can generate a cyclic pattern. In this case we know that it's a 256 byte buffer, so I'm going to specify, let's say 300 here. We generate the cyclic pattern and then we run the program. It asks us for the input, so let's paste in our overflow. Oops. And you'll see then that the program's crashed because we've overflown the buffer. It hasn't, the characters that we entered haven't arrived in the instruction pointer because it's 64-bit, so it doesn't actually try to load an invalid address like that. So we can just look at the first 4 bytes in the stack pointer and see, if we look up the cyclic-l to look up the offset of that, and see that that's at 280 bytes in. So we would need to write 280 bytes before we could overwrite the return address and redirect the execution to some other address in the program. But obviously in our case, if we go up and have a look here, it's printed out to say the code that we entered equals this, and we wanted it to equal dead beef. So when I was initially trying to solve this, I kind of figured that we should just overwrite this code with the correct value, because this is placed on the stack, and then we have our buffer as well. So if we overflow this enough, we'll be able to write over code. But I wasn't able to get that working. Let's test that out anyway. So we can see here that this is the value that we have in there at the moment. We could take this and convert this into ASCII, and just go to ASCII to hex quickly. We could convert this to ASCII, and then if we were to take this, we'll see that actually, let me check cyclic -L. Oops. And obviously that's way too far. Let's try and see if, so if we swap that round, we'll see that because of the little endian issue, we had to reverse the hex values that came out there. But that's telling us that we can write 280 bytes to overwrite our return address of the instruction pointer, or we can overwrite 268 bytes to get to our code variable, which is what we want to write dead beef in. So we could go and test this out. Let's go and try this quickly. So I'm going to do Python, make sure it's Python 2 as well, and we'll print out, doesn't really matter too much here, we can print Python 2, by the way, just so that it prints out the hex values correctly. So we can print out, let's say 268 times A, and then we'll do dead beef as well. We need to do it in reverse order, so \EF, \BE, \AD, \DE, and if we print that out, you'll see that we're not able to copy and paste this. So let's print it to a payload, to a file, just call it payload, and let me minimize this so we can see the terminal a little bit more clearly. Now we can go back to our GDB and we'll run the program again. This time we're going to send in the payload, and if we do that, we'll see that we have here our code is equal to dead beef, which is what we want, but we also have the 414141 at the end, which is our A's. So I tried to get around this by using some different values here to see, you know, if we could send in like null bytes, or NOP instructions. But yeah, it represents it as the ASCII value. So I couldn't get this to work, and obviously I was kind of looking around to see how I could do this for a little while, and then just figured, well, we have control of the instruction pointer anyway, and we have our system cat flag.txt in there, so let's just take a shortcut, or maybe the intended solution. Maybe this isn't, maybe this is just kind of a rabbit hole, I'm not too sure. Maybe somebody can let me know in the comments, did they successfully just overwrite this? I also tried adding in the new line as well, but yeah, I couldn't get that to work. So let's instead, let's do this. Let's find out where we want to jump to first of all. So if we go back to, or if we can do info functions. Okay, we're going to get a lot of functions now. Let's just disassemble the main function. And we know that we want to call system, which is right here. And before we call system, we need it to pop the cat flag.txt into the RDI. So we look for that instruction, we see that that's here, it's going to load that here. Before that we have a put, so I'm just going to grab this address. And we could go back and we could just do this manually first of all. So we can do 280, and we'll go back to the A's, and then we'll enter in this address instead. So \x 79, \x 07, \x 40. We may need to pad that as well. \x 00. Let's see. Let's try and run that again with the payload. We get an invalid address. Okay, we'll try and pad it with 5 sets of zeros. Oh, that was 4. Okay, but that did work. So it did try to cat flag.txt. In this case, we don't have a flag.txt, so we could create one if we wanted to test it out and just say this is a fake flag. And if we save that and run it again with that payload, oh, it's no longer set to... Okay, we need to set the file again. It's now the file is set to cat, so we need to set the file again to chal, and we'll try that again. And there we go, there's the fake flag. Alright, so that was a little bit of messing around to get that to work, but let's go and do this in PwnTools anyway, which is how I initially solve this anyway. I kind of think it's good sometimes just to go through and test this out manually, but let's go and check out the PwnTools script. So I'll open up the finished script here. This is just based on the PwnTools template which I use, which is linked down below on my GitHub. And some people like this, some people don't. Some people think there's too much code in here, but I like it for a couple of reasons which I'll describe. But if you decide to use this template, essentially just remember that most of your exploit, your exploit goes here. That's all you need to know. You'll be building up your payload here, so everything up top pretty much stays the same. And the reason I like this is because whenever we launch the script, so we can launch the script with Python final.py, but if we decide to, if we want to debug it with GDB, we can just add GDB in capital letters at the end, so we can say Python final GDB, and any breakpoints or whatever we want to put in here will also automatically launch them whenever we enter that. So it's quite easy then to just, we can test something with GDB and then quite quickly go back to testing the normal script without having to comment out different pieces of code or change pieces of code. And similarly, we'll be able to swap between local and remote just by using a keyword, which we'll see at the end of this as well. So that's one of the reasons I like that. I've also added in a function to find the instruction pointer. So the way we found our offset of 280, we can do that automatically here, and that's we don't need to do that. It's quite easy to find it manually, but it's just a way to automate things if you choose to. And then this is the only part of this that you'll ever really change, apart from maybe GDB scripts. So this is just the file name and then your log level. So we can set this to info and run the script, and we don't get too much information here. But if our payload wasn't working and we wanted to try and find out what's going on behind the scenes, we can set this to debug and run it again, and we'll be able to see everything that's sent back and forward and try and work out is something not aligned correctly, are we not reading in some lines that are being sent by the server, etc. Because sometimes swapping between the local and the server version, there can be some minor changes that need in terms of reading lines and sending lines. So with that out of the way anyway, let's actually have a look at the payload. And the payload is very simply here. We're finding our instruction pointer. We're giving it a cyclic pattern of 300, so it'll find out that that's at 280, which it did whenever we ran it there as well. You can see that we have 280, so it found out the offset, and that means whenever we're building our payload, we can just say that whatever we want to inject it at this offset. And in this case, I've just grabbed the address that we used whenever we did this manually as well. Because this is a single stage payload as well, you can also write this to a file, so we could then just send the payload off to the server if we wanted to. And then finally we're actually sending the payload off here as well. We receive a few lines because it sends a few lines back, and then finally we get our flag. But if you weren't just reading a flag here, you could also do IO interactive if we were getting a shell instead. But with that out of the way, we've done that, we've tested that locally. Let's see how easy it is now to swap between the remote, local and remote. So we can go here, we can just grab this netcat server and port, and we can run the exact same script but just paste in remote or type in remote and then paste in the server and the port, and we get back our flag very quickly. Just as a quick bonus, we could have a look at another way of doing this as well. So if we wanted to, we could have a look and see what ROP gadgets are in the file. So let's check the chal, and we'll see all the ROP gadgets here. If we want to search for some, for example, PopRDI, and we'll have the address here. So we could take this address as well because we know this is hard-coded, and we can specify it here and say our PopRDI gadget is equal to 0x and that address. And instead of just jump into that address, we could build up that payload manually. So in this case we don't need to because we have the system cat flag.txt here. But say we only had system and it was calling something else, it was checking the date or something like that, we might want to just pop our own string into the RDI, which would be the cat flag.txt, and then call system. So in that case, we could go to our payload, and at the offset here, we'll send a list instead, and we want to pop RDI, and what we want to pop into the RDI is going to be the string, so it's going to be our cat's flag string, and then we're going to call system. And we could find the address of system quite easily, but we can also, just because we're loading the binary in PwnTools, we can actually just say here elf.symbols.system, and that'll do the same thing. The only other thing we need is our cat, is to find out where the flag string is. So there's various ways we can find this. If we wanted to find it manually, like the PopRDI, we could use something like readelf, or we could do this in GDB as well. So if we go back to, let's open up GDB, PwnDbg, and we need to start running the program, but we'll set a breakpoint at main, run the program, and then we can search. So let's run search and check the help options, and we can see that we can search for strings here. So let's search for the string cat flag.txt, and we'll find that we have this address right here, so we could take a copy of that and say then our cat flag is equal to that address, and this should do everything for us. It should pop the cat flag into the RDI and then call system, which will then look for the parameter in the RDI as per the conventions. So if we try and run this now, let's go back and run it again. Okay, so that's a perfect example of running into a problem and switching to debug to see what's going on. And if you're going to have a look and see what's happening now, oh, it received the flag. It crashed after that by the looks of it. Okay, so in this case we've received too many lines by the looks of it. Let's change that to 3, and there we go. Okay, so that worked for us, and that was an example of what I mean. Sometimes you just have to swap between, because we changed our payload there, we had to swap that around a little bit. But that's one way to do that. Let's see as well, rather than using this cat flag here, we could do search, or is it next? Elf.search, and then we can search for cat, well, I think we want the whole thing, bin cat flag.txt. Let's try that as well, see if that works. It didn't work, it didn't find it. Let's go and have a look why not. And we'll see, okay, it didn't have bin cat, that doesn't exist in the program, so we just need cat. So let me try that again, and if we run that again, this time we do get the fake flag. And just in case you're not bored of seeing different ways to do this, let's see what else we could do. So rather than, we could actually search for this PopRDI, we could search for these gadgets using ROP objects, but we can actually just automate the whole thing using ROP objects. So if we say ROP is equal to ROP, pass in the elf, and then we can say, we know that we can do ROP.system because we know system exists, and then we can just pass in this next elf.search flag.txt, and that's going to basically build this all up for us, so that all we need to say is at this offset we just want to send ROP.chain, and that should work. Let's test that out as well. That works fine also. If we want to see exactly what's happening in the background, let's try and pretty print ROP.dump, and we'll see here that it's basically built up the ROP chain for us. So it's found the PwnDbg gadget, which is at 833. So you see, instead of doing that manually, it's found it for us. It's found the cat flag.txt at this E3D address, which again we have manually here. So we can take all that out, and we can now just automate that whole thing. And even this payload, I mean, the payload there we don't have to do too much, so we could just put that into one line really, and we don't even need to send it as a payload. We could just put that in here, take all of that out, and we've got a very short payload to send off. And that's been the first challenge. A few ways to do this. If you like this template and want to check it out, you can have a look on the GitHub.